Now I want to summarize this lecture. Initially, we talk about the expression of the electric field for a wave propagating along the z direction. And then once we put the Gaussian solution into the Helmholtz equation, we come up with this complete solution. And one term propagating along plus z direction, the other term propagating along minus z direction. And so you have to be careful about the sign before the propagation constant. And once you know the direction of the electric field, you can always calculate the direction of the magnetic field by using this expression. So in this lecture, we talk about polarization of the wave. And the polarization of an electromagnetic wave is defined along the direction of the electric field. And that is because once the electric field direction is defined, and we know the direction of the propagation of the wave, the magnetic field is already fixed. For example, we use the wave propagating along z direction. And suppose you have an electric field along x direction, then you can determine that the magnetic field will be along y direction. Conversely, if you have a wave propagating along minus z direction, but still have an electric field component along x direction, you'll be calculating an magnetic field along minus y direction. And so from here on, when we talk about polarization of a wave, we just talk about the electric field direction of a wave. And we continue to give some arbitrary component of the electric field on the xy plane, and we can always decompose the electric field into two components, one along x direction, the other along the y direction. And in general, the two amplitude along these two directions are going to be different, and the phase between these two components could be also different. And the phase difference here we denote it with the phi. And we found that this expression in fact tells you the tip of the electric field of this wave will trace out an ellipse on the xy plane. And this ellipse has a slant angle equal to this expression. And you found that to fully describe this polarization state, you only need the amplitude of the electric field and also the phase difference between these two fields. And so you can sort of reduce this quite complicated expression to a short notation called the Jones vector. You can just keep the amplitude of the electric field and also the magnetic field, and also the phase difference between them in this expression, and then you can fully describe the polarization state of this wave. So the simplest polarization state is called the linear polarization. For linear polarization state, you have electric field on this xy plane for a z propagating electromagnetic wave. And if you express the electric field on this plane, then you will find that the angle between this electric field vector and the x-axis is going to be fixed over time. This means that the electric field direction does not change with time, and we call this linear polarization. And for linear polarization state, the Jones vector is quite simple. You have just the real expression here and also real expression here, and there's no phase difference between them. And now, if you allow this phase difference to be plus minus 90 degrees, then we also found that the tip of this electric field will trace out an upright ellipse on the xy plane if this EX0 and EY0 are different. And the Jones vector expression is shown here, and just take a note that in front of this EY0, the amplitude of the y component electric field will have plus minus j before it. And the ellipse is described by this elliptical solution. It tells you that the x component of the electric field along this x-axis, which is the major axis of this ellipse, is just the coefficient, just the amplitude of this the x component electric field. And along y direction, the minor axis, the amplitude is equal to the amplitude of the electric field along y direction. And if you allow the time to tick, and the electric field vector on this xy plane will start to rotate, and the angle of this the electric field with respect to the x-axis can be calculated by taking the ratio of the electric field along y direction to the electric field along x direction. And the plus minus sign in front of this arctangent will tell you the sense of the rotation of this electric field. And for example, if you pick up this plus sign for your calculation, then this electric field is going to rotate along the counterclockwise direction. If you pick up this minus sign in your calculation, then this electric field vector is going to rotate along the clockwise direction. And for this two rotation directions, you can use your right hand or left hand to describe it. If you point your thumb along the z direction of the axis. And so for this case, we call this left-handed polarization. For this case, it's called by right-handed polarization, because you can use your right hand or left hand to describe the rotation direction. But remember that when you try to use the right hand or left hand, you first have to point your thumb toward the direction of the z-axis. And then we specify that the two amplitude of the electric field component along x and y direction to be the same. They are both denoted by E0. And then you come up with the circular polarization state. And don't forget that we still fix the phase difference to be plus minus 90 degrees. And this circle is described by this expression, and this is the well-known expression for a circle. Also, you can calculate the angle between the electric field and the x-axis by taking the ratio of this y component to the x component, and you come up with this expression. And again, this angle will change over time. So if you pick up this plus sign for your calculation, then this alpha angle is going to increase with time. So you will get this right-handed polarization state. But if you pick up this minus sign for your calculation, so when time increases, your alpha will become more negative. So you will end up having this left-handed polarization state. So this is about everything I have told you in this lecture. Thank you for your attention.